So there we go. What happens to profit as volume changes? And of course, that change in volume will drive changes in profit as it drives changes in costs, at least in variable costs. So speaking of that, let's first look at variable and fixed cost behavior. Some of this you've seen in economics, and you will be seeing it again in managerial finance. In fact, most everything in this chapter you will see in managerial finance, and I cover a little bit more than what we have in our textbook, which is good because that's going to give you a head jump on managerial finance. And people tend to find finance a lot easier when they cover these topics in there as a result. So variable and fixed cost behavior. Well, first we know that with variable cost, total variable cost changes in proportion to changes in volume. This because there's a uniform or constant amount of variable costs per unit volume. For example, let's say that we were manufacturing garments. We had $10 of fabric in each garment. That means if we make one garment, that direct materials cost, which by the way is an excellent example of variable cost, direct materials and direct labor both are. Well, if we make one shirt, we have $10 in materials cost. If we make two shirts, we have $20. Make 10 shirts, $100 of direct materials costs, etc. So there's a constant amount or uniform amount of variable cost per unit, which is 10. And then total variable cost goes up in direct proportion to changes in that volume. So we can plot total variable cost, and I will show you in just a second. And if we use the same scale for both axes of the graph, variable cost per unit will be the slope of total variable cost. So variable cost, if we were to plot that, it's going to look just like we have in our textbook. This is on page 1089. So if we look here on the Y or vertical axis, we have, in this case, they put the cost of batteries. Okay, these are batteries for tablet computers. So we have dollars here on the Y or vertical axis, and we have volume, number of tablets produced here in this case, on the X or horizontal axis. So as we make more and more of these, our total variable cost keeps going up. So variable cost starts from the origin, or 0, 0, an ordered pair, 0 first on the x-axis, second on the y-axis, another 0. So you may recall that from geometry. You don't really need to know it from this class. And also from geometry, starting as a ray from the origin. It starts right there at the intersection and goes up in a straight line. That's a ray. Let me just come down to something for a second. And if we look here at this little table on page 1091, with variable cost, we're reminded that total variable cost changes proportionally to changes in volume. So when volume increases, total cost increases. Excuse me. When volume decreases, total variable cost decreases too. But variable cost per unit remains constant or uniform. Now, coming back here, I have a little formula to figure out the slope or variable cost per unit. Variable cost per unit is always the slope of the variable cost line because variable cost per unit is the rate of change. So for every additional unit that we make, the change in total variable cost is variable cost per unit. So slope or rate of change, same thing. Well, this equals the change in total cost or total variable cost. I'll show you the total cost line in a few minutes, divided by the change in volume. And we can bear in mind the total variable cost equals variable cost per unit times volume in units. And we'll see in just a few minutes that the change in total cost, we'll have a graph for that too, equals the change in total variable cost, excuse me, as the graphs of the two are parallel. And I will put this formula to work in just a little bit. Then fixed costs. Well, in contrast, fixed costs will not change in total over the relevant range, which we always assume that we're in. And we can plot total fixed cost. So we'll see the changes in volume have no effect on total fixed costs as long as we're within the relevant range, ceteris paribus, which is a Latin term that you see in economics, which means all other things being equal. And we'll note here the total fixed costs will not change as volume changes, but we could say that fixed cost per unit will change inversely to changes in volume. So let me show you that back in the book. So here we have a graph or plot of total fixed in this next chart. And in this case, this company's total fixed costs are $13,500. So as long as we are within the relevant range, that has no relation to volume. So it is simply a flat line. Total fixed cost is constant. So coming back down to their little chart, they remind us that fixed costs in total are constant as volume changes. Then fixed cost per unit changes inversely, it changes in volume. Well, when volume increases, fixed cost per unit is going to decrease. That's because we are dividing a numerator of total fixed cost, which stays constant, by volume. If volume is increasing, we are dividing by more and more. So fixed cost per unit is going to go down. And conversely, when volume decreases, fixed cost per unit increases. Now, the term total cost. Well, since all costs are either fixed or variable, we can represent a company's total cost as follows. Well, total cost will equal total fixed plus total variable. Or if we expand total variable, equals total fixed plus variable cost per unit times volume. And we can always graph total cost once we know total fixed and total variable. And let me just see if there is one here in the book. Bear with me a second. Oh, I've got one right here. Good. All right, they don't show us total variable on this graph. The picture, if you will, total variable cost starting again at the origin, right at the intersection of the X and Y axes, and running parallel, to the graph of total cost. And this total cost, we see that the y-intercept, where it intercepts the y-axis that is right at the amount of total fixed. The reason being that if we had no units, 0 units, we're still stuck with total cost. We're still stuck with total fixed cost. But we will have no total variable cost. But then, as we produce more and more units, the amount by which total cost will increase will be variable cost per unit. Again, the same as that of total variable cost. So that's why total cost and total variable, if we had it here, will be parallel, just to let you know. So again, total variable cost, the y-intercept is at 0, and total cost at total fixed. Then second, total variable cost and total cost are always separated vertically by the amount of total fixed. That's the difference between the two, because we add in, you can see it right here in the equation, total fixed cost. So this implies that the slope of total cost is the same as the slope of total variable cost. And that equals variable cost per unit, of course. And up here, the way that I represented the total cost equation, total cost equaling, well, if you skip over here to the second iteration, total fixed plus variable cost per unit times volume. Well, I've really represented that as the standard equation that we have seen in geometry and also in algebra, where y equals a, or depending upon your textbook, alpha, times b or beta, or in some textbooks, m times x, where y equals total cost. A or alpha equals total fixed cost, which is the intercept parameter. In other words, the y-intercept of total cost. And b or beta or m equals variable cost per unit, which is the slope parameter. And x again equaling volume in units. So what I have here is again parallel to the second iteration of total cost. Then there are two ways to estimate a cost function. First of all, linear regression. It's the more accurate way. It's discussed in your quantitative methods or business stats course. I don't need to do it here. But just to let you know, there's a quick and easy method that we will use just to give you a feel for this, which is called the high-low method. And it's a quick method of estimation. It's going to use the highest and lowest observed values of the cost driver. Make sure you use cost driver. I'll show you why in a second, to form a line which approximates the total cost function. It works when we have only one cost driver, which is what we will assume. We assume that our cost driver equals number of units. So to do this, we're going to calculate two things. The slope, or variable cost per unit, which equals the change in total cost or the change in total variable cost, divided by the change in units, just like we saw above. Of course, those two lines have the same slope. Then second, total fixed cost is going to equal total cost minus total variable cost. And total fixed cost will be the same both the highest and lowest points, of course. If it's not, we've got trouble. So let's see an example of this. If we go north on 98 from Lakeland, we go past the Lakeland Square Mall, which I haven't been to in a long time, and you probably haven't either, we would hit the Little Selma of Gibsonia. So if we go there, let's assume that we have the Gibsonia Gasket Company. If you're wondering what a gasket is, you could look at the inside of your refrigerator or freezer door. That's a gasket that is there to seal the door shut, usually made of either rubber or plastic. So let's assume they've got the following data from the first 5 months of the year. And we'll estimate its cost function using the high-low method. So we've got 5 months, we have total costs, we have unit sales volume. So what we want to do is to go for the high and low of the independent variable, or in other words, volume. So number of units, X. So if we look, we've got a high here of January, and we have a low, looks like May. Well, I'll tell you what we should do. And let me see something in here. Give me a second, and there we go. Okay, I didn't plot these, but if I did, May would not fit the pattern. So if we were to plot these data points as you've done before in other classes, we would find that May is just totally outside the overall pattern. It's a so-called outlier or a fluke. It just doesn't work. So we would throw it out. Trust me on that, since I didn't plot these in a scatter diagram for you. Anyway, we want to go for the next viable low. So throw May out. You can see it's really unusual. Total cost only $11,000, totally outside the others. So May's a fluke, throw it out. The next low that we would have would be March. Let's use it instead. So again, notice I went for the low of unit sales volume as well as the high. I'm just going to consider these 2 points and fit a line between the two of them. Make sure that you do not go for the high of total cost, That's the dependent variable. You don't want to do that. You want to go for the high of the independent variable, which is unit sales volume. I threw February in there deliberately to illustrate that point. So back here on the printed solution, which I have of the outline examples, it's in a PDF file, which is also on Canvas for you. Again, the high is January. I have an ordered pair of what's on the x-axis first, 6,000 units. Then what's on the y-axis second, 27,000 units. So the order is first X, then Y. Then the low of March. Again, I have an ordered pair. 3,000 units on the x-axis, $18,000 on the y-axis. The slope. Well, if I take the difference between either total variable cost or in this case, total cost, well, the high of total cost is $27,000. The low is $18,000. So sometimes we call that the run. I'm sorry, sometimes we call that the rise, because that is the difference in the y-axis. How much things go up on the y-axis from $18,000 to $27,000. So that is a rise of $9,000 if we subtract. The run, or difference in the y-axis, run being horizontal. Well, we have $6,000 minus $3,000. So up top, we have $9,000. At the bottom, we have 3,000 units. So we're really saying that this increase of $9,000 is due to 3,000 units. Or if we divide on average per unit, that's $3. So $3 is the slope of total cost. It would be the same slope of total variable cost. And that is, of course, unit variable cost, $3. So every additional unit we produce causes total variable cost to go up by $3. Then total fixed. I could take the high and find it. So I could take $27,000 minus a computation of total variable cost at that point, which would be 6,000 units times $3 a piece. So I'm saying the total cost minus the total variable cost component equals total fixed of 9,000. I should get the same result below. $18,000 of total cost minus, here's total variable cost, 3,000 units times $3 a piece, again giving us 9,000. If I did not get the same answer both ways, I need to go back and check my work. So it's a really good idea to go ahead and compute total fixed cost both ways. So therefore, the total cost equation equals total fixed of 9,000 times 3x. 3 being, again, the slope parameter or variable cost per unit, and again, x being unit volume. So that's the high-low method. Again, quite a simple method there of computing our total cost equation. So let me ask, do you have any questions at this juncture? Does it make sense? All righty. And I realize you've got this here as backup. Since I don't have a blackboard here to write everything on, well, this will be the next best bet. I can have one of those little handheld chalkboards or whiteboards for markers, but again, for accounting, I wouldn't have a lot of room on one of those either, would I? So these PDFs are the next best bet. All righty. Again, if you have any questions, just stop me as I go along. Now, for just a few moments, let me relax the idea that everything is either a fixed cost or a variable cost. So let's have some other possible cost relationships. Well, first of all, a mixed or semi-variable cost has both a fixed element and a variable element. So what we have for a mixed cost is the total mixed cost equals total fixed cost plus total variable cost. Excuse me. The difference from a company's total cost and its total a total mixed cost is that a mixed cost is just a little component of total fixed. I'm sorry, back up. Is that a total mixed cost is a little component of total cost, just a little one. Let me show you an example here in the book. And it's about a company's cell phone bill. Actually, I cheated and I used their graph to earlier illustrate total cost. So what we have here is that we've got this sample company again, Smart Touch Learning, here in Exhibit 20-4. So it shows how Smart Touch Learning can separate its cell phone bill into fixed and variable components. So the cell phone bill is a really good example of a mixed cost. Again, one little chunk of a company's total cost. And the $100 monthly charge is the fixed cost because it's the same no matter how many units the company uses the cell phone. So that's the fixed cost. But then they have a 10-cent per minute charge as a variable cost that, of course, increases in direct proportion to the number of minutes of use. I don't know why they don't have an unlimited plan, but they don't. So if Smart Touch Learning uses the phone for 100 minutes, its total variable cost is $10. So 100 minutes times 10 cents per minute. Quite easy to find. It's rather like a company's total variable cost once again, same sort of equation. And we see that if it doubles used 200 minutes, then total variable cost also doubles to, in this case, well, 20 minutes. 200 minutes at 10 cents per minute, and the total bill rises to $120. So this graph here is showing total cost from the cell phone bill, and it looks just like total cost from the overall company. The only difference is the numbers are much smaller. So it's just one little component of a company's total cost. So I don't have to spend a whole lot of time on mixed costs. They're quite easy, but that's what they look like. And any questions there about mixed costs? All righty. Let me come back here to the outline. And another type of cost we have is a step cost in number 2. Step costs are fixed for small ranges of volume within the relevant range, but the increase in a step-like fashion as volume increases. And step costs have characteristics of both fixed and variable costs that makes them rather difficult to analyze in our earlier format. And the key is to very narrowly define the relevant range. And they're illustrated in Exhibit 20-5. By the way, I earlier found I had a typo there. I had 18-something. Whoops, I didn't update that from the old edition of the book. This used to be in Chapter 18 there. So please make sure that your copy says 20-5. One little problem, I don't know why the textbook doesn't call these step costs, but, well, in their infinite wisdom, they didn't. So let me show you that. I come down, here we go, on page 1094 to a step cost. So this exhibit is going to show fixed costs in a step-like fashion for Smart Touch Learning over 3 different relevant ranges. And if the company expects to produce 2,400 tablets next year, the relevant range is between 2,001 and 4,000 tablets. Here is why. Because one worker can produce up to 2,000 units. So if they did that from 0 to 2,000 units, we would need one worker. That worker would have a cost of $81,000. That's the little relevant range for up to 2,000 units. Then, if we produce from 2001 to 4,000 units, we need 2 of these workers. So the fixed cost doubles. They're getting a salary, not a wage, to $162,000. But then if we step up to 4,001 to 6,000 units, Well, we need 3 of these workers. So the total cost goes up, total fixed cost goes up to 243,000. So we can say the fixed cost is on each of these little relevant ranges, each of these little steps. So it looks just like a flight of stairs. And so we have to very narrowly define where we are on this. So we have to be even more precise about our relevant range for a step cost than for a regular fixed cost. Again, you can see why this is called step cost. Looks just like some steps there. Then, lastly, another type of cost relationship is a batch cost. And that involves a set of costs for each batch of production or batch of purchases or sales. So we're switching, for example, from one type of unit to another type on the assembly line. So if we do, we have to stop, reconfigure our machines, put new direct materials on the line, etc. So the cost to switch from one type of unit to another type, one type of product to another type, that would be a batch cost. So we would simply add that into our total manufacturing costs. So our total manufacturing cost would still be total fixed plus total variable plus, in this case, the number of steps or batches times the cost per step or batch. That's all it is. We just augment that equation a little bit. So no questions so far. Alrighty. So moving on down here, I'd like to introduce the contribution margin. So let's see what that is. Well, in this chapter, we're going to be concerned with period costs or expenses. And the volume that we will examine is measured as the number of units sold. And we'll assume this equals the number of units manufactured. After all, if we have a true just-in-time system, what we produce is exactly what we sell. So we're going to assume that. So sales volume equaling production volume in that case. And thus our usual revenue driver and expense driver will be the number of units sold. And we'll concentrate on the special case of one product rather than on the usual case of a sales mix of different products for simplicity. So we'll calculate things, including the break-even point, in just a little bit for one product line at a time. That illustrates all the points we need to know about cost volume profit analysis, because if I tried to do this for multiple products at one time, it would get too complicated. So we don't need to do that. Besides, if we're doing that in business, we'll have a computer to help us. So here's another good benefit of this. In the case of one product, a unique break-even point can be computed. So I definitely want to be able to do that. Now, in B, I'm going to go back to considering how all expenses considered in this chapter. I'll get my water bottle open. I hate these because the plastic is very thin these days, speaking of products using less in the way of direct materials, and the bottle is a direct material, also using less in the way of direct materials in terms of the cap. Caps are smaller, they're harder to get off these days. As we try to get them off, we usually squeeze the bottle and, well, some of it leaks out. Let me just take my cap off. I'll be right back. Good, had to go grab a towel to do that. Well, we look at C here, and I'd like to talk about a company's income statement. Two different formats that we can use. So we can do it either under a functional format, like we did in financial accounting in 2111, or on a contribution margin format, which I will introduce to you here. You'll also be using the contribution margin format in both cost accounting, if you take it, but all of you will take managerial finance, so you'll use it in there too. We're going to note that operating income is the same under both formats, But gross profit, sometimes called gross margin, is going to differ from something called contribution margin. I will show you. So as an example, let's go up to North Florida, to Lake City. If you've driven on 75 up north, you've driven through Lake City. So we've got the Lake City Lock Company, and it manufactured and sold 2,000 locks last year at a mean sales price of $9 each. I'd like to keep numbers small, they're easier to deal with. We see that variable manufacturing and variable upstream and downstream costs, we could also call those variable operating costs, are $3 and $1 respectively. And total fixed manufacturing costs and fixed upstream and downstream expenses, or we could say operating expenses, same thing, or even selling and administrative expenses, they're $2,500 and $1,500 respectively. So let's prepare an income statement under both the functional and contribution margin formats. So I will show you. Let me do the functional format first. And for this, I'm going to come back here to this outline, and let me actually come down here to C. I'll come back here to what I have in B in just a few minutes. Decide to take them a little bit out of order. I think that'll make a little bit more sense here as I do this remotely. So first of all, the functional format for the income statement. This again is what we did in 2111. It's going to separate costs by function. That's where it gets its name. Into either manufacturing costs, we could also say cost of goods sold, or as upstream and downstream costs, or operating costs, or as selling and administrative costs. So here's what it's going to look like. First, I've got sales revenue. 2,000 units times $9 a piece. Whoops, forgot my closing parenthesis there. $18,000. Then one way that costs behave is as manufacturing or cost of goods sold. Some are variable, some are fixed. So variable manufacturing, so that would be direct materials, direct labor, and variable overhead. 2,000 units, $3 a piece. We were given those numbers again, or $6,000. Then fixed manufacturing costs, we could also say fixed overhead, $2,500. And I put those, as you see in a left-hand column, I bring the total over to the right of $8,500. So that left-hand column gives me further detail. This gives me a gross profit or gross margin of $9,500. Then I subtract the other way costs behave as upstream and downstream, again also known as selling and administrative or operating costs. Again, some are variable, so 2,000 units times $1 a piece, 2,000 bucks. Some are fixed, we're told 1,500. We know fixed will not depend upon volume. So that's a total of 3,500 of upstream and downstream costs. We subtract, we get operating income of $6,000. Now, let me do, for this same company, the contribution margin format. This will separate costs according to behavior, either as variable or fixed costs. So I've got the very same sales revenue figure up top. Then I subtract variable expenses, and these numbers will be very familiar because we just had them. 6,000 of variable manufacturing, 2,000 of variable upstream and downstream, giving us $8,000. If I subtract that, I get a figure called total contribution margin. Now, the other thing I do is to subtract the other way costs behave, which is as fixed costs. So fixed manufacturing, $2,500, fixed upstream and downstream, $1,500. Again, the same numbers I had on the previous income statement. 4,000 bucks that is of total fixed. That gives me operating income of $6,000. That number looks familiar too. But the only thing is, again, I have simply recategorized my expenses here. Here's why this will be good for us. If I look here above fixed, so everything total contribution margin above, all these, as volume changes, these will change. We will then subtract a band of fixed expenses which do not change as volume changes. Then that leaves us with operating income, which will change as volume changes. And I'll show you an example in just a couple of minutes. We'll really highlight those facts. Now, total contribution margin, how does it get its name? Well, total contribution margin, as you can see, represents the amount of sales dollars that we have left over once we covered our variable expenses. And it really is named because it contributes toward covering fixed expenses and then contributes toward providing for a profit. So, does that make sense? Okay. Now, the next thing I have here is called the contribution margin ratio. It equals contribution margin divided by sales revenue. And we can compute the contribution margin ratio for the Lake City Law Company on both a total dollar basis and on a unit basis. And we're going to note that we get the same answer both ways. So with this, let me go back here to my handwritten example solutions. And I look here at contribution margin. Well, on a total dollar basis, it would be $10,000 of total contribution margin divided by $18,000 of total sales revenue. Well, per unit. Okay, our sales price is $9. That would be sales revenue per unit. Up top, I've got contribution margin per unit. How did I get that? It equals the price of $9 minus variable cost per unit. So we had $3 for manufacturing and $1 for upstream and downstream. So 9 minus $4 of variable cost equals $5 of contribution margin per unit left. Either way, we're going to get 0.555 repeating decimals, so a bit over 55.5 cents as contribution margin. Again, if we do it on a total dollar basis or on a unit basis. So we're really saying that out of every sales dollar, a bit over 55.5 cents will be left over as contribution margin. So a bit over 55.5%. You'll see why we need that in just a little bit. Let me come down for a moment to F, the variable cost ratio. That equals, well, it's going to look a lot like contribution margin ratio. It's going to be total variable cost divided by sales revenue, or 1 minus contribution margin ratio, because out of every sales dollar, something is either variable cost or it's contribution margin, since we're subtracting variable cost from our sales revenue figure. So let me come back to my handwritten solution page here and look, whoops, just under this here. There we go. Variable cost ratio. So in our case, a total of $4,000 of total variable cost divided by $9,000 of sales revenue. That equals, well, reduces to a fraction of 4/9, which will sound familiar because $4 is variable cost per unit, $9 is price per unit. So it equals 0.444 repeating decimal. So we're saying that out of every sales dollar, a little bit over 44.4 cents is going to be eaten up by variable costs. Or, well, in proportion, a bit over 44.4% of our sales revenue will be eaten up by variable costs. Again, this equals 1 minus the contribution margin ratio. So 1 minus 5/9 equals 4/9, or again, 0.444, repeating decimal. So we'll need that number in just a little bit. So a couple of easy ratios there. Now let me come back to E. Well, changes in volume, at least within the relevant range, induce changes in operating income. And that's due to changes in total variable costs and changes in sales revenue. So in this example here, we're going to prepare pro forma, which by the way, pro forma means as if. It's a Latin term. Contribution margin income statements for the Lake City Log Company for 1,000, 2,000, and 3,000 units. So as if we sold 1,000 units, as if we sold 2,000 units, as if we sold 3,000 units. We're going to assume the sales volume equals manufacturing volume. In fact, we always will in this chapter. And we can note that the differences in operating income at each volume level equal the differences in total contribution margin. So let me show you that. Again, going back to my handwritten solution here. So in this, I've got 3 sales volume levels. Again, 1,000, 2,000, 3,000 units. Our sales revenue of $9 per unit, I simply multiply units by $9 to get each of those sales revenue figures. I then subtract variable expenses, manufacturing $3 per unit, upstream and downstream $1 per unit, again multiplying by the number of units to get the totals. Then total contribution margin, which is $5 a unit. Again, $9 minus 3 minus 1. So I could take my $5 and multiply by the number of units going across to get total contribution margin. The other way I can get is top down by taking the sales revenue figure and subtracting total variable cost at that point. So this gives me total contribution margin of $5,000, $10,000, and $15,000. I then subtract manufacturing costs and upstream and downstream costs in the way of the fixed components. So the other way costs behave as fixed versus variable up here. So constant bands of $2,500 and $1,500. This gives me operating income figures of $1,000, $6,000, and $11,000. So again, we note that everything down through total contribution margin changes as volume changes. Total fixed cost do not change as volume changes. Operating income will change as volume changes. In fact, we can note this. By the way, the triangle, which is the Greek letter delta, that it means change. So the change in total contribution margin equals a change in operating income at each of these levels. And it also, the change in total contribution margin also equals the change in units times the unit contribution margin. So the change in units from column to column is 1,000. In fact, we can note that 1,000 units times $5 a piece, sure enough, gives us a change of 5,000 units a pop up here. We can also notice the change in total contribution margin equals the change in revenue times the contribution margin ratio. So the change in revenue is $9,000 a pop. If we multiply that by the contribution margin of 5/9, we'll get a change in revenue, sure enough, of $9,000. So again, I messed up. The change in, the change in total revenue is $9,000 a pop. If we multiply that by 5/9, the contribution margin ratio, we'll get, sure enough, the change in total contribution margin from column to column of $5,000. And again, any change in total contribution margin equals a change in operating income. By the way, if we take away that change sign, We could say that total contribution margin equals unit sales volume times unit contribution margin. Sure enough, if we multiply $5 up here by the number of units, we'll get total contribution margin. Also, total contribution margin equals total revenue times contribution margin ratio. So if we wanted, for example, to take total revenue of $27,000 here, if we multiplied by 5/9, we would get $15,000 as total contribution margin. And we can also note this finally. Total contribution margin from the bottom up equals total fixed cost plus operating income. So just go up, add 1,000, 1,500, 2,500, you'll get 5,000 here in the first column. And also total contribution margin, we see in the second iteration of the equation, equals total revenue minus total variable cost, which is the top down. So in this first column, $9,000 minus 3,000 minus 1,000 gives us 5,000 bucks, sure enough. So it's just good to be able to work with those numbers for when you take managerial finance later. And we can also note the following over here for variable cost. The change in total variable cost equals the change in volume times unit variable cost. So change in volume or change in units is 1,000 bucks from column to column. If you multiply by variable cost per unit of $4, you'll get a change in total variable cost of 4,000 bucks between each column. It also equals the change in revenue times the variable cost ratio. So the change in revenue being $9,000 multiplied by 4/9, the variable cost ratio. And again, you'll get a change in variable expenses column to column of $4,000. Then finally, if we take away the change, total variable cost equals unit sales volume times unit variable cost. We already know that. And also equals total revenue times the variable cost ratio. So I'll let you double check those later if you'd like. All right. Any questions? Okay. So just come back and work with this a little bit, but it's making pretty much sense so far. Okay, good. All right, good. Took care of all that. Just one thing I'd like to go back and do. Something that I skipped for a moment. Why don't I appear at the top of the second page? Excuse me. What I have here is that we could consider this equation. Operating income, what does it equal? It equals TR, total revenue, minus TVC, total variable cost, minus TFC, total fixed. Those acronyms are not surprising. Or if I expand total revenue to PX, price, times unit sales volume, P unit price, X unit sales volume. If I expand total variable cost to VX, or unit variable cost times X sales volume. Again, minus total fixed costs, leaving that as a constant. I can then factor an X out of these two. So I have that operating income equals unit sales volume times P minus V times price minus variable cost per unit minus total fixed. Well, this component right here will make sense to us. X equaling unit volume, P minus V equaling unit contribution margin. So the unit contribution margin, in our case, that was $5 times X, which is unit volume, equals total contribution margin. So just like in the first column where we sold 1,000 units, well, if I have $5 as contribution margin per unit, I multiply by $1,000, I'm sorry, 1,000 units, sure enough, I get $5,000. Whoops. mess up. Okay. If I've got, what I have, 1,000, yeah. So if I've got 1,000 units, so I subtract 9 price, V of 4, I have $5 as unit contribution margin. If I multiply by 1,000 units, I've got, as in the first column, total contribution margin of $5,000, okay? All right. Let me go ahead and move down to some profit planning here. And we'll have, again, a special case of profit planning where we have a profit of 0. So that's the break-even point. So let's see what that break-even point is. Well, the break-even point is the point at which operating income equals 0. So we don't make a profit, but we don't lose anything either. And in today's environment, a whole lot of companies would be happy just to break even because they're at a point of loss right now. So I will show you this graphically by superimposing a sales revenue function over our cost graph. Again, placing volume on the x-axis, we always do. And we've drawn that graph, well, on my PDF. And we're going to note in just a second the break-even point, the profit area, and the loss area. And we'll note the total revenue function is assumed to be linear, and it's a ray from the origin 2. This will allow us to find the break-even point graphically, and I will show you. So let me go ahead and show you that here on the PDF. It's right here in Roman numeral 3, part A. So what I did, I have the total cost line or graph here. Again, the y-intercept being total fixed cost, the slope being variable cost per unit. Then the total revenue line. It's a ray from the origin because if we have 0 units that we sold, we will have 0 total revenue. The slope or rate of change will be price because for every additional unit we sell, the rate of change of total revenue will be the price. So the slope of total revenue will be greater than the slope of total cost. It's because we want price for total revenue to be greater than variable cost per unit. Otherwise, we'll never earn profit. So eventually, total revenue is going to cross total cost. Where it crosses? Well, total revenue minus total cost, same amount. We have the break-even point because we have a profit of 0. So we can find the break-even point in terms of units. If we simply scroll down here to the x-axis. On the other hand, if we scroll over to the y-axis, we will have the break-even point in terms of sales dollars represented by B here. We'll find it in both. Now, if we look, this triangle down here, where total cost is greater than total revenue, represents the area of loss. So we could, if I were showing this on the board, I would draw here in big letters loss, L-O-S-S. Up here, where total revenue exceeds total cost, I would draw profit up here. By the way, I would draw profit in black, and I would draw loss in red, and I'll tell you why losses are often called being in the red or even shown graphically in red letters, red numbers. So the reason is that on an old ribbon for a typewriter or an adding machine, there would be 2 bands on it. Top band of black, bottom band of red ink. So black ink represented a positive number, red ink represented a negative number. So if a company says they're in the red, which many companies are right now, they have a loss. If a company's in the black, they have a profit because that would be shown as a positive figure in black ink. And that's also where the term Black Friday got its name, the traditional kickoff to Christmas shopping of the day after Thanksgiving, because for many retailers operating on very thin gross margins, very thin gross profit per unit, First time they earned a real profit was on Black Friday as people were shopping for Christmas. These days, Black Friday doesn't draw as many shoppers. There have been too many tragedies, quite frankly, in shopping in in-person stores, including one about 15, 16, 17 years ago here in Lakeland at the Walmart on South Florida, where suddenly they unveiled a product, shoppers started rushing toward it, someone was trampled, and no one stopped, even though she'd fallen, and she was killed. That's happened a lot on Good Friday sales. Well, just below this, I have a profit loss chart, sometimes called a PL chart. So right here would be 0, the y-intercept, the intersection of the x and y axis. So right there, we have no profit. Down here, we have a loss. Up here, we have a positive profit. So that's called a PL chart, just to let you know. Let's check something here. Good. Alrighty, back here to the outline, if we look at B. Well, going back to the contribution margin income statement, we can cast it into variables. This will look familiar, and this will allow us to find the break-even point by formulas. So sales revenue, PX, total variable cost, VX, then total contribution margin, just as I factored that out earlier, X or volume times P minus V. So I'm really saying total contribution margin equals unit volume times contribution margin per unit. Then subtract total fixed, leave that as a constant term, giving us operating income, OI. So let me find something called target sales volume first. So if a company wishes to earn a target operating income of OI, which we would be given, whatever it may be, it can determine the number of units it must sell by the following formula. It will equal total fixed plus operating income divided by the unit contribution margin. I'm going to calculate how many locks Lake City Lock Company must sell if it wishes to earn an operating income of $1,000. So let me come back here to the PDF and let me look specifically at this here. I'm going to derive the formula. It's not really necessary for this class, but it's very helpful when you get to managerial finance. So if I have an equation of, this will be familiar, operating income equals total revenue, PX, minus VX, total variable cost, minus total fixed. Or, again, if I factor an X out, X times P minus V, so volume times unit contribution margin, minus total fixed. That makes sense. Total contribution margin minus total fixed, sure enough, equals operating income. Good. So, where total fixed plus operating income equals total contribution margin, this iteration here being total contribution margin. So now, if I divide, I simply take this term on the right and put it under the term on the left. So total fixed plus operating income divided by P minus V, which again equals unit contribution margin. That is the formula that we have. So let me put it to work here. We've got total fixed of 4,000 plus this desired or sometimes called target operating income of 1,000 divided by $5, unit contribution margin, equals 1,000 units. So sure enough, if you double check on the pro forma income statement that we did earlier, if we have 1,000 units that we sell, we will generate an operating income of $1,000. So that's just what we want. Again, if you have any questions, just stop me. Well, then D. let's think about the break-even point. Well, since operating income is 0 at the break-even point, the formula for sales volume at the break-even point becomes this. Well, number of units, or volume, is X again. It equals total fixed plus, well, operating income just goes away because it's 0. Divided by the unit contribution margin. So let's compute the Lake City Lock Company's break-even point in sales. In units. So if I did that, again, back here on my PDF, again, we note that operating income equals 0 at the break-even point. Therefore, again, operating income just vanishes in the formula. So we take total fixed of 4,000 divided by $5, giving us 800 units. And if you set up a little pro forma income statement for 800 units, I say 8,000 a moment ago, 800, pardon me. And if you did that, you would find, sure enough, that you're at the break-even point. So your profit would be 0. Okay. Now, let's say instead of units we just did in these past two, we wanted to find the break-even point in sales dollars. We could definitely do that too. So we can find the break-even point in sales dollars using the following formula. Well, PX, or sales revenue, it equals total fixed cost divided by the contribution margin ratio. Okay, so again, nice to look at that formula, but if we can derive it, even better. That will help you out in finance. Again, you won't have to derive it in my class, but just want to show you anyway. Here on the PDF, on this 5th page, deriving the formula. Well, what I have here first is we can reflect on this. Total revenue, or PX, times contribution margin ratio equals total contribution margin. We've seen that. Well, total contribution margin, I could expand that. It actually equals total fixed cost plus operating income. We've seen that too. So now if I divide both sides by contribution margin ratio, so I flip it over, I'm left with PX over here on the left-hand side. On the right-hand side, I have total fixed plus operating income divided by contribution margin ratio. I'm really saying that this numerator is total contribution margin. And if I divide total contribution margin by the contribution margin ratio, I do get sales revenue. So the formula would make sense. Again, you don't have to derive it, but nice to be able to do so. So if I were to take my total fixed of 4,000 plus technically operating income of 0 at the break-even point, and I divide by 5/9, the contribution margin ratio, or 0.55555, if you like it better, I would get $7,200. Well, that makes sense because a moment ago, we said that the break-even point in terms of units is 800. Multiply 800 by 9, you get $7,200. So that 7,200 does make sense. We'll be at the break-even point there. Now, let me go to a non-zero operating income here in F. That'll be quite easy for us. Well, if the company wishes to turn a target operating income, OI, whatever that may be, we can compute the total sales revenue it must reach this way. Same thing as up here, but just add operating income into the numerator. So as an example, let's compute the sales revenue needed to earn an operating income of $1,000. So back here on my PDF, I've got that. $4,000 total fixed plus operating income of $1,000, again divided by 5/9. Contribution margin ratio gives us $9,000. And sure enough, that makes sense going back here to our pro forma income statement. If we sell 1,000 units, which translates into $9,000 of sales revenue, sure enough, we generate an operating income of $1,000. So that does make sense. And no questions so far? Okay. Now, in G, something that's related to break-even analysis is called margin of safety. Well, it's the amount by which sales exceed break-even sales. And stated differently, it's the amount by which sales can drop before the company incurs a net operating loss. So as an example, what is the Lake City Lock Company's margin of safety when budgeted sales equal 1,100 units? So let's see that on the PDF. I found it for you here in G. I've got budgeted sales minus the break-even point will equal the margin of safety. I've done that in terms of units and in terms of sales dollars by taking those units and multiplying by the price of 9. So in units, I have 1,100 units, or in sales dollars, $9,900, minus the break-even point of 800 units, or in sales dollars, 7,200. That looks familiar. Subtract, we get margin of safety of 300 units, or $2,700. So again, our current sales could drop by 300 units or by $2,700 before we get to the loss category, which of course we want to avoid. So it could drop by that much before we go from black to red. Okay, so it's a nice little cushion that we have so far. Then, final topic that I have here on our outline is called sensitivity analysis. This is done a lot in business because we like to look at what changes as some scenarios change. Let me show you. So sensitivity analysis means analysis of the changes in one variable which are induced by changes in the other variables or parameters in the model. So as an example, let's compute the break-even point in units and sales dollars, assuming the following independent assumptions. I've got 3 different scenarios. They are independent, which means that we will return to the original information for each and then calculate any changes from that original information for each scenario. And I will show you along the way. So what happens first of all, if this scenario happens in number 1, total fixed cost will drop by $500. Well, our new total fixed would be $3,500, goes from $4,000 down to $3,500. So I take $3,500, I divide by the unit contribution margin of $5. I get a new break-even point of $700, so it dropped because we don't have as many fixed costs to cover. In sales dollars, I could take $3,500 and divide by 5/9 contribution margin ratio, excuse me, to get sales revenue of $6,300. So again, it dropped because again, our total fixed cost dropped. We don't have as much to cover. Less in the way of total fixed cost is a good thing in that case. Now, let me come to the second scenario. What if the sales price increases by $1? So coming here to my PDF, the new price is 10, so it goes from 9 up to 10. Therefore, the new contribution margin ratio, well, the numerator is contribution margin per unit, which is $10, the new price, minus the same old $4 of unit variable cost. So it'd be $6 per unit. Or in terms of ratio, divide that by 10.6. So 60% of our sales revenue is left over as contribution margin. Or you can see on the other hand that out of every dollar that we sell, 60 cents will be left over as contribution margin. So contribution margin in terms of sales units, the number of units sold, sales volume. Go back to the original information once again. These are independent assumptions, so don't use 3,500 here. Go back to the original total fixed of 4,000. and divide by the new unit contribution margin of 6. It will give us 666 and 2/3 units, but we can't solve fractional units. So the next thing to do, round up. 667 units, we're not concerned about. A little bit of rounding error. We know what we're doing. Or in terms of sales dollars, $4,000 of total fixed divided by the contribution margin ratio of 0.6. And well, okay, that equals $6,667, $3 of rounding error. We don't care. Now, back for the last scenario that I have. Number 3, what if variable manufacturing expenses increase by $2 per unit? So again, let me go back to the original information. The new variable cost is 6. It goes from $4 up to $6. The new contribution margin ratio will go back once again to the original price of 9 in the original information. 9 minus 6 gives us contribution margin per unit of 3. Divided by 9, the new price is 1/3. So out of every sales dollar we sell, a bit over 33.3 cents will be left over as contribution margin. So a little bit over 33 1/3%. Now, this will equal, if we go back to a new break-even point in terms of units, well, take $4,000, again, the original total fixed, divide by the new contribution margin per unit of 3. That will give us 1,333 1/3 units. Can't sell a fractional unit, so let's round up. We always do that by convention. Will give us 1,334 units. In terms of sales dollars for our break-even point, we could take $4,000 and divide by 1/3, which would be the same thing as multiplying 4,000 by 3, giving us $12,000. And in fact, that takes care of everything in the chapter. So do you have any questions here? Anything I can help you with? Certainly is. Any questions develop, let me know. And if you have any questions on the homework in this chapter, sometimes they apply this and it might look a little bit difficult at first blush. I will be more than happy to go over anything with you. So always am.
Thank you so much.
Thank you, Amber. Thank you, Jen. So again, everything's okay so far. Just need to work with it maybe a little bit. Oh,
Yeah.
yeah. And again, this will help you out in cost accounting and will help you out in managerial finance. And you'll breeze through that stuff in those 2 classes. So not to worry. All righty. So take care, and I will look forward to seeing you Monday. It seems strange to say have a good weekend already, but, well, I know you will. Okay. Bye-bye. See you Monday.